Alright, so we're going to compute the area between f of x equals x squared and the x-axis from 0 to 1. We're going to do this in two steps. First, we're going to compute our n, and then we'll take its limit as n approaches infinity. Okay, so first we need delta x. Alright, so our rectangles, let's see, so we start at 0 and then we go over to 1 over n, then next 2 over n, then 3 over n. And we keep going like this, let's see, until we get to n minus 1 over n, and then n over n, which we know is 1. You could think of our starting point as 0 over n. Alright, so now remember that Rn uses rectangles whose height is the rightmost endpoint, or is f of the rightmost endpoint. Okay, so this guy, f of 1 over n goes there, f of 2 over n goes there, so that's our height of our rectangle. F of 3 over n goes there. And we continue in this way over to this last one. And so you see there are n rectangles here. Maybe n minus 1. Let's see, we had 1 there, 2 there, 3 there. Okay, so we have n rectangles. Okay. Okay, so now our n is the area of each of these rectangles added together, or the sum of the area of these rectangles. Okay, so this guy has width 1 over n, and his height, or length times width, his height is 1 over n squared. Plus again, 1 over n times 2 over n squared. Plus, again, this distance is 1 over n times 3 over n squared. This continues on until we get to this last guy, whose width is, again, 1 over n. And the height is n over n squared. So, n over n squared. Now the idea is we want to set up to use formula S2. Alright, so first thing we can pull out a 1 over n. Right, 1 over n is in each of these, so we can factor that guy out. Oh, this is a 2 over n squared plus 3 over n squared plus n over n squared. Using rules for exponents, we see we got 1 squared over n squared, 2 squared over n squared, 3 squared over n squared. Continuing on this way, n squared over n squared. Now notice that we could factor out, again, a 1 over n squared. That's 1 squared plus 2 squared plus 3 squared plus n squared. All right, I think some of you might be saying, hey, how did you do that? All right, now think here that this is really, we could think of this as 1 over n squared times 1 plus 1 over n squared times 2 and on like that, factor that guy out. Okay. Now 1 over n times 1 over n squared is 1 over n cubed. And using formula S2, we can now find another way to write that guy. Let's see. Sorry. Let's see. So formula S2, this guy becomes n cubed over 3 plus n squared over 2 plus n over 6. And now we want to set up to use L'Hopital's rule, which is a polynomial over a polynomial. So we need to get a common denominator. Let's see, this would be, the common denominator we can see is 6, so 2 there, and a 2 there, a 3 there, and a 3 there. Okay, so we have 6 on the bottom, 2n cubed plus 3n squared plus n. And so now multiplying these guys, we have 2n cubed plus 3n squared plus n over 6n cubed. So that's our Rn. Rn, this is the approximation using right-hand rectangles, where the height is taken using the height at the rightmost endpoint. So, and remember, in the last video, I tried to illustrate that as we increase n, the approximations get better and better and better. So it stands to pass that as we let n approach infinity, this thing will approach the area under the curve. So we go ahead and do that. Alright, now plugging in the infinity top and bottom, right, we get infinity over infinity. Because a polynomial with n cubed has n behavior like so. Right, so as n gets large, 2n cubed gets large, 6n cubed gets large. Okay. So we don't know what that means, infinity over infinity. So we can take the derivative, top and bottom. That's L'Hopital's rule. Let's see, we've got 6n squared plus 6n plus 1 over 18n squared. Again, we plugging in the infinity, we get infinity over infinity. We don't know what that means. Take the derivative top and bottom. Let's see, we got 12n plus 6 over 36n. Okay, again, we get something like infinity over infinity. So we take the derivative, top and bottom. Over 36. The limit of a constant is a constant. It's 1/3.